I'm Noah. This is joint work with Oded, Daniel, and Devesh. You'll hear from Daniel in a little bit when he talks about a nice extension of this algorithm. And I'll be showing you the state of the art in finding shortest vectors. So before we start, I should just give a disclaimer that this is not the fastest algorithm to break crypto. This is the fastest algorithm for the exact variant of this problem. For the approximate versions, we have slightly faster algorithms. So I just sort of want to make that disclaimer. I'm not claiming anything that's not true. This algorithm is very, very simple. So please interrupt me if you're not understanding, because you should be understanding. So with that, let's define a lattice. I think you guys all know this. It's a discrete set of vectors in Rn. Here's one in 2 dimensions. Looks like that. And it's specified by a basis. So here's a basis for this lattice. There are a set of linearly independent vectors. And the lattice itself is a set of integer linear combinations of the basis vectors. I think we've all seen this before. The shortest vector problem just asks us to find the shortest non-zero vector of the lattice, right? So the shortest vector in the lattice is 0. That's boring. The shortest non-zero vector of the lattice is very interesting. So here's it in this lattice, I think. This is known to be NP-hard, even to approximate, which is why I'm going to show you an exponential time algorithm. And just some notation, we'll write lambda 1 of the lattice to represent the length of the shortest vector. And I'm always talking about Euclidean norm. So for this lattice, this is lambda 1. This problem's received a lot of study. It's quite important. Works was sort of initiated by Kanan in '86 with an enumeration-based algorithm that ran in n to the n time, but interestingly in poly n space, which still makes it interesting today. And then a breakthrough work in 2001, Aitai Kumar and Shiva Kumar showed a sieving algorithm that ran in singly exponential time, which was a big open problem for a while, as you can see. And a lot of work was done to bring down the constant and the exponent. This is a small subset of the works on this. I think the current best with the sieving approach is 2 to the 2.5 roughly n. And then in another breakthrough result in 2010, Michancho and Vulgaris showed a deterministic singly exponential time algorithm based on the Voronoi cell for both SVP and CVP. So remember, Daniel's going to show you our CVP algorithm. So this algorithm was interesting both because it's deterministic and because it solved CVP and because it brought the constant and the exponent down now to 2. So this is a 4 to the n time algorithm. In this work, I'm going to improve things by a quadratic factor, so I'll show you a 2 to the n time algorithm. And for what it's worth, it's randomized. So the fastest deterministic algorithm is still Daniele's. That's the history. Here's our algorithm. So my primary tool is the discrete Gaussian distribution. So first I'll give you some intuition based on the continuous Gaussian distribution. So this is how I'll notate a continuous Gaussian distribution. It assigns to vector x probability proportional to its Gaussian weight, e to the minus length of x squared divided by s squared. So s you can think of as the standard deviation up to some constant factor. It's just a scaling factor. And all I want you to know about this distribution for now, so it looks like this roughly, and when I lower the parameter, it gets narrower. That's all I want you to know. So lower standard deviation, narrower Gaussian. So for a discrete Gaussian distribution, we simply assign weight proportional to the Gaussian mass of a lattice vector now. So now y is the lattice vector, that's why it's red. And we're just going to take the distribution that assigns Gaussian weight to each vector. So for fairly high parameters in 2 dimensions, it looks like this. It just sort of looks like a pixelated Gaussian distribution. But if we lower the parameter, of course, as you might expect, it gets narrower. If we zoom in a bit, we can see that it's sort of lower resolution now. Sort of the set that it's supported on is now, in some sense, sparser. If we keep going, it sort of looks less and less Gaussian. If I go even further, then things get sort of silly. Now it's sort of only supported on really 9 vectors. And if I go further than that, then things just get ridiculous. Then I'm just sampling 0. But I want you to pay attention to this parameter. So things are rather misleading in 2 dimensions. But the thing to notice here is that this is a shortest vector. So if I were to sample from this distribution on this 2-dimensional lattice, I would get a shortest vector with fairly high probability. We're trying to solve the shortest vector problem, so this is good for us. Of course, in higher dimensions, things might be a little messy, but the intuition that we can take from this is that if we get enough samples, where I'll define enough in a second, from the right parameter, I'll define that in a second too, but it's rather small, then we can sample from then we can solve the shortest vector problem. In particular, if you use a rather heavy hammer, so I certainly won't show you this proof, you can show that we need about 1.38 to the n vectors, with s about lambda 1 over square root n. So polynomial factors won't matter to us much here. So basically, you want to sample from a parameter proportional to the shortest vector. And this uses the Kissing number bound of Kabatiansky and Levitstein. Now, for very high parameters, the discrete Gaussian is extremely well studied. In particular, above the so-called smoothing parameter, which I won't define formally, but intuitively it's when it looks like a Gaussian. So at the beginning, I showed you a sort of very nice pixelated Gaussian distribution. That was above the smoothing parameter. By the time I got to these sort of weird distributions, no longer smooth. And in particular, Gentry, Peikert, and Vaikuntanathan, who are all here, showed how to sample in this regime in polynomial time. So above smoothing, at least well above smoothing, we know how to sample from this distribution. But previously, even in exponential time, there was no algorithm to sample below smoothing.
Do we know what the length of the shortest vector should be?
So we can guess it. I mean, also, we're going to go down in sort of increments, so we could just sort of take the shortest vector that we happen to find. But yeah, we can just guess it up to like some small factor. But good question, yeah. So just to hammer this home, this nice, smooth, pretty distribution is easy to sample from. This weirder distribution is hard to sample from because it has a much lower parameter. And there's a natural question, which is, can we use samples from the right-hand side or your left-hand side to get samples from your right-hand side? So this is going to be our goal, right? So we'll call this converting Gaussian vectors, by which I mean sort of lowering the parameter. And we're going to do this sort of incrementally. And again, we'll take our intuition from the continuous Gaussian distribution. So if I sort of give you oracle access to a continuous Gaussian distribution, and I want you to output another continuous Gaussian with the parameter lowered by some factor, what would you do? There's an extremely simple answer. Did you have a question? Okay. There's an extremely simple answer, which is to divide by 2, right? So it's a very simple property of the discrete Gaussian that if I divide by 2, I get another Gaussian with smaller parameter. So we can ask if this works in the lattice case, right? So here's the discrete Gaussian. Can I divide by 2 and get another discrete Gaussian with a lower parameter? So the answer is, of course, no. And the reason is quite simple. Let's say I sampled this vector, and then I take half of it. Half of it's not even in the lattice, right? So this fails rather tremendously. So that's not going to work, but we can imagine getting around this by conditioning on the result being in the lattice. So it turns out that if we do that, we get the right distribution. This is just the formal statement saying that we get the right distribution, right? So probability that y over 2 equals some vector x, conditioned on it being in the lattice, is proportional to the Gaussian mass. But now we have this nice factor of 4 in the exponent, which is progress. That means that we've lowered the parameter by a factor of 2. But unfortunately, this requires us to throw out a lot of vectors. Indeed, when we're above smoothing, this requires us to throw out to only keep like 1 in every 2 to the n vectors. We want to do this a few times, super constant number of times, so this isn't going to work for us. But now we can consider another way of converting Gaussian vectors. We can consider, I'm just going to sort of tell you this because I don't know how natural it is, taking their average. Right? So if you take the average of 2 Gaussian vectors, the result is, again, a Gaussian with the parameter lowered now by a factor of square root 2. So we can ask the same question about the discrete Gaussian. If I take their average, is the result another discrete Gaussian with the parameter lowered? And the answer is, again, no. Right? So take 2 vectors, take their average, not in the lattice. Same problem. So it seems like we haven't gotten anywhere, but I'm giving you this talk because we did get somewhere. So we can ask, what about conditioning on the vectors landing in the lattice? And now I'm going to give you a sort of proof by picture. So the question is, if I have 2 vectors sampled from the discrete Gaussian with the same parameter, and I take their average, and I condition on the result being the lattice, what do I get? And here's my proof by picture. Before the proof by picture, sorry. let's ask just when we have y1, the average being in the lattice. So I have two lattice vectors. I can write them in terms of the basis. That's the definition. So these are integer coordinates. And I can write their average in terms of the basis. When is the average in the lattice? So when these are integers. So when are these averages all integers? It's just exactly when all the coefficients have parity. The corresponding coefficients have the same parity. Right? Another way to say this is that y1 is equivalent to y2 modulo twice the lattice. This is just sort of algebraic way of saying this. So just to hammer this home, we have that the average of two lattice vectors is in the lattice if and only if they lie in the same coset mod twice the lattice. And there are 2 to the n cosets, one for each parity vector mod n. So this is like one of the most technical parts of our algorithm, I swear. So we can imagine, instead of when we sample a pair of lattice vectors, we can think of this as sampling from the product lattice. So L times L, this is just the Gaussian's invariant under taking products. It's still a Gaussian. So here's L cross L in 2 dimensions, because that's the best I can do, or rather in 1 dimension, because that's the best I can do. And in 1 dimension, there's only 2 kinds of parity. There's even and there's odd. So we're interested in vectors whose coordinates have the same parity. So here are the vectors whose coordinates are all odd. Here are the vectors whose coordinates are all even. And we're going to throw out the rest. So this is sort of what we get after we condition. And you can note that this is also a lattice. I'll call it L dagger. So it's just a set of points y1 and y2 that have the same parity. And here's my proof by picture. It turns out that you're looking at this in the wrong way. You should be tilting your head sideways. So I'll do it for you. If you tilt your head about 45 degrees, or I rotate it about 45 degrees, or exactly 45 degrees rather, you see that what you get actually after this rotation is a product lattice. So this is actually L times L scaled up by a factor of square root 2. This is what makes our algorithm work. This is nearly the whole proof. So why is this helpful? So this means that if I sample y1 and y2 from this L dagger, yeah.
Say what the algorithm is? Because
No. No, I'm showing you that this conditional distribution is right, and then I'm going to show you how to sample from it. So if I take y1 and y2 from L dagger, discrete Gaussian over L dagger, and I rotate it, this means I get the discrete Gaussian over this product lattice. And this is just saying that the discrete Gaussian is invariant under rotation. Gaussian measure is invariant under rotation. Now I can just write down what this rotation is. This is the rotation that I just showed you. It's the first coordinate is y1 plus y2 over square root 2, and the second coordinate is that. And the thing to notice is that the first coordinate looks a lot like an average. It's just scaled wrong. So in particular, if I instead took the average and I threw in that second coordinate, which won't be important to us, that's the same as rotating and dividing by a square root 2, which means that if we take the average, then the first coordinate will be distributed as a discrete Gaussian on L with the parameter dropped by a factor of square root 2. So that shows that this conditional distribution, if we take the average of 2 lattice vectors conditioned on the result being in the lattice, the result is, so the square root 2 is progress. And if we condition on the result being in the lattice, when we take the average of 2 lattice vectors, the result is again a discrete Gaussian with the parameter dropped by a factor of square root 2. So we're now left with the question of how do we sample from this conditional distribution. So let's just sort of write down the probability that we get, the probability that the average of 2 lattice vectors equals some value conditioned on them landing in the lattice. So this lands in the lattice exactly when they're in the same coset, mod 2L. So this probability, the probability that y1 is in a given coset is actually going to be proportional to the weight of the coset squared. It's essentially collision. Right? So this is going to be the sum over cosets of the probability that a discrete Gaussian vector lands in the coset squared times the discrete Gaussian sort of over the coset. But the important thing to note is that this weight of the cosets is squared here. So this suggests an algorithm, and this is almost exactly what we do. Our input will be roughly 2 to the n samples from DLS, think sort of asymptotically a bit larger than 2 to the n. We're then going to separate the vectors into buckets according to their coset. So we expect, as long as the cosets have roughly even weight, we expect to have some vectors in each coset, in each bucket. And then we're simply going to pair a number of vectors from each coset proportional to the size of the coset squared, the number of vectors that we got in the coset squared. So this squared corresponds to that squared. And then we're going to output the averages of the pairs. So this pairing is what gives us this, yeah?
Cosets of what?
Mod 2L.
Oh?
Mod 2L of the vectors y. So I have a bunch of vectors y that I sampled from the discrete Gaussian. I can look at their coset mod 2L. I can group them by those cosets. And then if I take the average of two vectors in the same coset, that will land in the lattice, right? And I know that if I take this conditional distribution, so I condition on them landing in the same coset, then I get a discrete Gaussian with the parameter lowered. This is just a trick to sample from the conditional distribution much more quickly than you'd get otherwise. It's sort of amortized.
Number of cosets is 2 to the n?
2 to the n. Yeah.
So before you had the sum and the difference of these two vectors.
Yes.
Now the difference disappeared. You only have the sum.
We could take the difference too. It's just.
So why did you draw the difference up at all?
Well, I think the only way that I know how to give this proof by picture is working in 2 n dimensions instead of n dimensions. So you get this extra difference. Yeah.
You can win a little, right? I mean,
Yeah, I can win a factor of 2. Yeah, but I'm hiding things that cost us like a polynomial factor. So the factor of 2 is not going to be important to us. Yeah.
Step 2.
Mm-hmm.
The random step is step 2.
Yeah, so, well, also, no, so we sampled originally. So this is, and it turns out that the way that we really do step 2 is random, because we're actually going to do this probabilistically, so we get an exact thing, not an approximate.
Step 2 mean now? When you say pair a number of vectors.
So now I'm just saying there's some proportionality constant. I have this list of numbers, and I'm going to, from each bucket, I'm going to take a number of pairs that's proportional to this size. And I'll tell you the proportionality constant exactly now. Or,
So step 1 is very BKW-like, right?
So
Step 2 is the new. Is something weird going on?
no, but
yeah,
you two things that have the same coset when you add them together, so it sort of cancels out the join.
But he's doing it proportionally. I mean, he wants to get a Gaussian.
yeah. I mean, this is similar to like a lot of, I mean, similar to sieving algorithms in some way as well. Like, I think what's new here is that we really decide to control the distribution. So our output is Gaussian, and we figured out that this is a way to do it with proof by picture. So I have the number of vectors that I output is going to be some proportionality constant t times the sum of the size of the coset squared, right? So what proportionality constant t can I take? Well, I want to take the largest one possible, and the largest thing that I can take is 1 over the size of the maximal coset. If I take anything larger than that, then I'd have to output more vectors than I have. That's no good. I'm leaving out a factor of 2 here because I'm taking pairs, but we don't care about factors of 2. But we know the distribution of these vectors, so we know roughly what this will be. If we start out with m input vectors, then this will be roughly m times the sum of the probability that we land in this coset squared divided by the maximal probability of a coset. So this is a collision probability divided by a maximal probability. Right? And I think cryptographers are fairly used to seeing things like this. You can think of this as Renyi entropy compared to min entropy. So we know that actually this can be quite bad. So the worst case ratio here is actually 2 to the n over 2. So I can lose, my sort of loss factor can be 2 to the n over 2 here after a single step, which seems really bad. Remember that when we had a loss factor of 2 to the n before, we threw that algorithm out immediately. So now we have 2 to the n over 2. We saved a factor of 2, but that doesn't seem quite enough. So now we panic, but I'm talking to you, so something works out here. And this is really, really magical. This is the most technical part of the talk. I think I said that earlier. It was false.
So far.
Oh, yeah. No, this is the most technical part of the talk, I swear. Daniel's will be more technical. So I have this collision probability divided by this maximal probability. And I just want you to note that this collision probability, we actually gave this a name earlier, right? So we have this sort of collision lattice, this L dagger that I named earlier. So this is just the Gaussian mass of L dagger divided by the Gaussian mass of the product lattice, which is just the mass of the lattice squared. But I also have a very nice identity on L dagger. I know that the Gaussian mass of L dagger is the Gaussian mass of this scaled up product lattice. And now I'm just going to rewrite this. This is the same as the Gaussian mass of the lattice squared with a factor square root 2 now in the parameter. So I've now simplified well, arguably simplified. The numerator, the denominator, it turns out, I'm just going to tell you this. If you've seen lattices, discrete Gaussian at all, you know this, but if you haven't, just take my word for it. It turns out that the central coset has the maximal mass. So the central coset is 2L. So particularly, the probability of the central coset is the weight of 2L divided by the weight of the whole lattice. So the weight of the whole lattice cancels out, and this is the final expression that we get. Although, just to write it slightly differently, I want to take that 2 and put it in the parameter. So this is our loss factor. And again, this can be as bad as 2 to the n over 2. But now I'm going to consider the loss factor over many applications. So I'm going to run this algorithm many times, and these parameters here, this is just saying that my parameter goes down by a factor of square root 2 every time. So remember that I'm going to apply this many, many times, and each time my parameter goes down by a factor of square root 2. So this is the loss factor that I get from running this L times, I guess. But note that this is a telescoping product. So in fact, almost everything cancels. And you're left with just a ratio from the beginning and a ratio from the end. Everything else cancels out. That might be slightly too complicated for you to see right now, but I promise I didn't lie. And this last factor here, this is actually greater than or equal to 1. In reality, it's basically 1 for our purposes, but this is greater than or equal to 1. So what matters is this factor here, and this is a fairly standard bound proven originally by Banachik. You can see this intuitively just by pretending that this is a continuous Gaussian. If this were a continuous Gaussian and this were an integral instead of a sum, then the factor that you get here would be 2 to the minus n over 2. And it turns out that lattices are bounded by that. So in fact, this loss factor is no worse than 2 to the minus n over 2. So I started out by telling you that the loss factor in one step can be 2 to the n over 2. I'm now telling you that the loss factor in L steps is also at most 2 to the n over 2. So somehow we have this magical property that no matter how long I run this, the loss factor is never worse than the worst case loss factor in a single step, which we don't understand. We have no geometric interpretation of this proof. The proof is really quick. We don't understand why it's true, though. Now, if I start out 2 to the n vectors, which I need to start out with, at the end, I'll get 2 to the n over 2 vectors. This is multiplication. And remember something that I told you earlier that you probably forgot. We only need 1.38 to the n samples to solve SVP. 2 to the n over 2 greater than 1.38 to the n. So as if by magic, we've solved the problem. So that was probably a little fast. Let me show you the final algorithm. It's fairly simple. So here's our SVP solver. We're going to first use GPV to get about 2 to the n samples from the discrete Gaussian with some fairly high parameter, significantly bigger than lambda 1. We're then going to repeatedly run this sort of squaring, combining process on the result. So we're going to group everything by buckets. We're going to take values proportional. We're going to take from each bucket a number of vectors proportional to the square of the size, and we're going to take averages of the resulting vectors. And then if we do this the right number of times, and again we can guess the right number of times, then we get to output 2 to the n over 2 samples from DLS with the parameter now much lower. So the proof that I just showed you shows that this is actually what we get, that we get 2 to the n over 2 samples, and that the parameter has dropped as we want it to drop.
Don't you have a problem with independence?
No. Well, okay, the way I showed it to you, yes, but we use a thing called the Poisson trick. I don't know if you've heard of it, but it's a way to get it to take a multinomial distribution and convert it into a bunch of independent Bernoulli distributions. So we have a multinomial distribution over the cosets, and then we get a bunch of independent Bernoulli distributions over the coset. So we have no independence issues at all. There's a small error that we get from that, but it's like 2 to the minus n squared if you want. So it doesn't matter. And then, because of the fact that we know we only need 1.38 to the n vectors to get a shortest vector, that means that if we just output the shortest non-zero vector from our samples, with overwhelming probability we'll get a shortest vector. So that's the full algorithm.
So does this mean that you can start from less than 2 to the n vectors? If
No. No. So in order to do my bucketing, when I'm above smoothing, I actually need 2 to the n. I mean, even like polynomially more than 2 to the n. Yeah. So our running time is really 2 to the n, and I don't see an easy way around that.
So now, how did you actually get all the way from something huge to what you want?
Well, I have this, like, the factor goes down by square root 2 each time. So
Do it iteratively, or you do it?
yeah, I'm doing it iteratively. I'm doing it repeatedly.
Okay, I see. So
Yeah, I do it over and over and over again. Yeah, exactly. So like I have.
You do 2 to the n samples, you combine them something, you get smaller number of samples, and you try to combine them again. And so
Yeah. So there's something that I was hoping to gloss over, but somehow magically it works out that if you look at the loss factor after I steps, we end up getting exactly the number of vectors that we need to fill the buckets in the ith step. So some buckets are going to be totally insignificant because they have really low probability, and it works out for, again, reasons that we really don't understand so well, that we always have the right number of vectors.
But the actual algorithm is like you sample them and you group it, you get this vectors in this whatever double or whatever the, and then you pretend that those are your new samples, and again
well, I take the average and then I pretend they're my new samples. Yeah.
And then you collapse them
Do it again.
into new packets and so on.
Yeah.
And you're saying at the end you do it enough steps, you still have 2 to the n over 2 samples, even though in one step you might have 2 to the n over 2 then.
Yeah. I mean, I'm hiding additional loss factors, so we can't really run it forever. But yeah, essentially.
So do you use less samples if you want to get not the shortest version of the sample?
No. So again, just to start out, I need 2 to the n. Yeah. So I'll tell you in a second that we have a kind of way around this ish, but it's not what you're thinking.
You can do a reversible approach, right? Just try to shoot for a vector which is not that short and use it to get a better approximation for the Gaussian.
Yeah, so we had this algorithm at some point, but it turns out it's simpler just to start out with a pretty good basis. So at the beginning, we start out with a pretty good basis, so that our samples aren't that far above lambda 1 to begin with, actually.
So now also this question. So in this probabilistic analysis, you were paying attention to the square of the bucket size.
Yeah.
But at the end, don't you just end up taking all possible combinations? So you actually...
No. I throw out a lot of vectors. In fact, I can throw out like a 2 to the n over 2 fraction of the vectors in one run. I throw out a lot of vectors.
So you actually really do the sampling according to the right distribution, and then you keep doing sampling as opposed to just taking...
Yeah. I think that that's the big difference. Like if you want to view this as a sieving algorithm, which some people do, then that's the big difference between our approach and the other approach. We care about the distribution, so we just throw out vectors to get the right distribution. We also don't pay attention to the length of the vectors at all. I never mentioned the length of a vector in the algorithm.
Maybe you just say again what's the policy for when you throw out the vector when you actually use it?
So, I mean, the rough idea is that I want to output a number of vectors proportional to the square of the size, right? So let's say there are 2 buckets.
Where did that come from?
That came from the fact that this conditional probability is like a collision probability. So it assigns weight squared to each coset. And I know that this conditional probability is exactly what I want by that sort of rotation proof.
I think this was actually Evgeny's question, but I just wanted you to answer again.
Yeah.
You have 2 to the n samples in the first step, and you throw
Yeah.
a lot of them. You still need 2 to the n samples in the second step.
Yeah, so that's... The answer is that I really don't. Yeah, so I only lose if the vectors aren't if the buckets aren't roughly uniform, and if they're not roughly uniform, then in the next step, the sort of ones that were far off from uniform are going to be totally insignificant. So it turns out that sort of like exactly the number of vectors that I lose, or the number of vectors that I'm left with, is exactly what I need to fill up the remaining sort of significant buckets.
Is it related for the same reason as the telescoping product, or is it?
Yeah, I think, yeah. I mean, the reason for the telescoping product is a mystery to me, but yeah, it follows from the same algebra, yeah.
So the number of samples you really need is not 2 to the n, it's 2 to the n.
It's 1 over the probability of the maximal bucket. So basically, I need enough samples to make sure that the maximal bucket will at least have some weight. That's all. Yeah. So like if they're uniform, then I need 2 to the n. But if they're not uniform, then I can need much less than that.
So in this gap between 1.38 and 1.44.
This is a coincidence. Like, yeah, there's no reason why that's true. I mean, the kissing number bound. Like, I don't think people think it's tight. It's just what we can prove. Yeah, I don't think there's something deep going on there. It's rather convenient for us.
Large gap, you cannot like optimize it and get something fast.
We don't know how. Yeah, I mean, it would save us like 0.3 in the exponent or something like that. But yeah, we don't know how.
Use this as an approximation algorithm. It seems like there's a trade-off between running time and the quality of the approximation. You just run it so far, you run out of vectors.
Yeah, it doesn't matter how long we run it, though. We're going to run it like polylog n times. We don't. So we run it so little that, so the loss factor from the things that I showed you is bounded, and then the loss factor from things that I didn't show you is going to be like 2 to the pi log n, which we don't care about. So yeah, I mean, I guess you could save like in the little o of n in the exponent, but other than that, yeah. But I will show you something that does do that, like right now almost. So I showed you in this talk a 2 to the n time algorithm for SVP. I actually showed you something slightly better, which is a 2 to the n time algorithm for discrete Gaussian sampling for any parameter s that actually gives you 2 to the n over 2 vectors. So this is sort of an amortized algorithm, but just to hammer this point home, we don't get 1 vector in time 2 to the n over 2. We get 2 to the n over 2 vectors in 2 to the n time. But there is an additional result from this work which uses the same idea but is significantly more complicated, which gives us a 2 to the n over 2 time algorithm that actually samples 2 to the n over 2 vectors also. So it basically loses nothing, but except for little of n factors. But it only works above the smoothing parameter. Although usually when people say above the smoothing parameter, they mean like root n times the smoothing parameter. We mean actually square root 2 times the smoothing parameter. So this buys us a lot. It gives us a 2 approximation to the decisional variant of gap SVP, like you were saying. It also lets us solve BDD to pretty damn close to the unique covering radius, and it gives us root n log n SIVP. We can probably do better than that. And to reach an additional result is that I actually showed the other direction. This is just a preprint right now, but actually the discrete Gaussian sampling reduces to shortest vector problem, which I found to be very surprising. This is not an equivalent because the other direction, yeah. Okay. This is not an equivalent because the other direction is an exponential time. I actually don't think that these problems are equivalent. I suspect that discrete Gaussian sampling is not NP hard. In fact, that's one of my open questions. And because I'm a little over time, I'll just sort of show these and I'll talk about them. So thank you very much. And here's a short vector. Daniel's going to take a second to set up, so if you have any more questions.
So one comment first. So one of the reasons previous work was sampling above the smoothing parameter. It was not just because people didn't know how to sample below it. So there was another reason, which was the primary one.
Actually, no, sorry, I disagree.
I think that people were doing that because that's what you needed to prove the average case result.
But yeah, no, I mean, I agree that nobody saw a need to go below the smoothing parameter, but everything prior also incurred error that depended on.
Oh yeah. So those algorithms don't work, but the primary reason people were looking at that one. That's
agree. Yeah.
So my question is, can you get some other average case result, maybe for some other distribution where A is not uniform out of this?
I'm not sure. My guess would be no, because like I don't see a polynomial time reduction coming out of this. Yeah.